You may recall from our series circuits lessons a scientist named Kirchhoff who had a voltage law for series circuits. And it was called Kirchhoff's voltage law. Well, as it turns out, Kirchhoff actually had a second law called Kirchhoff's current law, which applied to parallel circuits instead. We actually proved it, believe it or not, in our previous video. And so I wanted to make a video sort of explaining the current law and the different ways to write the formula. In fact, there are actually 3 ways to write the formula. So let's talk about each one and what they mean. And the first way to write the formula is pretty self-explanatory, pretty easy. If we have a parallel circuit, we have multiple routes for electrons to take, we have multiple currents. And the multiple currents combine to make our total current. In other words, current total equals current 1 plus current 2 plus current 3, and so on and so on and so on. And however many resistors we have is how many currents we add up, or how many paths, I should say, of resistors is how many currents we add up. We can actually rewrite this formula another way. And the way we do that is by assuming we know that current is the exact same as voltage divided by resistance, which is what this magical little symbol means. This equal sign means you can literally replace one with the other. So we can rewrite current total as voltage divided by resistance total, with the resistance total, of course, being what these 2 individual resistors sort of combine to running in parallel. Well, we can rewrite current 1 as voltage divided by resistor 1. And then we can rewrite current 2, so plus current 2, as voltage divided by resistor 2. And of course, if we had multiple pathways, we would continue the formula on with however many paths we have. And I'll go ahead and add a plus sign here so we can see that the formula is actually continuing. But as you can see, the current is changing proportionally with the resistance. And so since they're both changing together, the voltage is remaining constant, which is why we have the same voltage for each individual current when we do our math. When we did our math in the last video, you might have noticed. And in a later video, we'll explain more in detail on exactly how the voltage is constant in a parallel circuit. But for now, let's just assume that it is constant, looking at this formula. And then let's cancel out our voltage. So cancel out voltage. And then if we cross out voltage on each individual one, all we're left with on top is essentially 1, because 1 times voltage is voltage. So we're left with 1 on top, and then resistance total on bottom. And then, of course, here we're left with 1 on top and resistance 1 on bottom. And again, plus 1 on top plus resistor 2 on bottom. And of course, if we had more than 2 resistors, then the formula would continue like before. But essentially, these are the 3 ways to write Kirchhoff's current law. So we can even say 1, 2, 3 ways. And so while we're at it, let's go ahead and define Kirchhoff's current law and its implications. So the actual law is just the first formula, and that is the individual currents, or we'll say in a parallel circuit, the individual currents combine to the total current, or let's say add up to the total current. And of course, its implications are simply the other, sorry about that noise, are simply the other 2 formulas. That's what the implications are. They're just the other formulas. So the first one is voltage is constant, and I can't stress this enough. It's only constant in a parallel circuit. And of course, the last implication is this last kind of weird resistance formula that we just proved. And that is just saying that the total resistance is equal to the inverse. And that's what this means. 1 over resistance total is the inverse of resistance total of the sum of the individual resistors' inverses. And again, this is individual resistor 1 and individual resistor 2, so 1 over R1 is the inverse of resistor 1, and 1 over R2 is the inverse of resistor 2. So let's go ahead and finish writing this out. The total resistance is the inverse of the individual resistors' inverses. So let's write this out correctly. Resistors inverses added up. Which is, again, all this last way to write this formula is saying. You're adding up the inverses to get the inverse of the total resistance. And in the next video, we'll explain more in detail exactly what this means and how it looks, how to use this formula.